Alright, so this is where we left off in the last video. The basic idea is, using filters, you can, figure out the temperature of a star, right? So just using filters and not, using the spectrum of a star to find its peak wavelength, which is quite involved. It's much simpler to just measure the filter the light, the visible filter and the violet filter, and then use that to estimate what this or give you what this curve will be. All right. So anyhow, we already talked about that. So that's what we do in general. All right. So a long time ago, it was actually over 100 years ago, people started looking at the spectrum of stars, and there was actually this some ladies working for Harvard, the Harvard Observatory, and they were classifying. There were literally hundreds and hundreds, if not thousands, of spectra. And at first they just labeled them, this looks like, we'll just put this in pile A, pile B, pile C, and so forth, right? And then one of these ladies, named Miss Cannon, actually decided correctly to classify these according to their temperatures. And so when you classify them according to the temperatures, things start to make a lot more sense. And so those piles, had already been established for quite a while. And so they just took, what was originally called the O stars. Those are the hottest stars. And then comes B stars, A stars, F stars, G stars, K stars, M stars. There's also like L and T. I'm not sure I don't think we're going to talk about those right here. All right, so this is the original categories of these 7 different stars, and we break these down. There's in between like an O and an O star and a B star. There are like 10 numbers as well. All right, so there's a mnemonic, by the way. Let me go over that mnemonic for remembering this order. Astronomers learn this very, very early in their career, and so here's how it goes. So it's OBA, fine, and so it's guy or girl depending on your preference. Kiss me, and so it's a very clever little mnemonic. Obia, fine, guy or girl. Again, that's kiss me. All right, so that's just a simple little way of remembering the order of the stars. And remember, O stars are the hottest. M stars are the coolest. There's actually two, as I said, there's 2 categories beyond this. This is the classic, the classic temperature range. Just to let you know, our sun is a G-type star, and so we'll further categorize it. So these are the categories. All right, let's keep going. So there's some things that you'll notice. Take a look at this picture here. So one of the things about O-type stars is they're hot enough to actually ionize helium. This is the B-type. So you can see this is the temperature of the O-type stars. The temperature of B-type stars is given on the left-hand side. G-type stars. Notice this is the range. The sun is just around 5,000. There's a range of these, by the way. It's not just one particular temperature. So the sun is 5,800 Kelvin. K stars a little cooler, M stars even cooler, and of course L and T stars even cooler than that. So these are the general. Again, this is just talking about some of the different absorption lines that are observed. So again, ionized helium. Okay, so that's a thing that a big thing that characterizes O stars. The only way that you're going to get helium to ionize, helium's a very stable atom. It's one of the stablest atoms on the periodic table, and it really likes to hold on to those two electrons. So you have to get temperatures, around 30,000 Kelvin or so before you can ionize helium. All right, so the next one, of course, B stars. There's you get some ionized heavy elements, and there's some hydrogen. Notice you get pretty much neutral helium. So sometimes some of the helium will be ionized. Remember, these temperatures that we're talking about are generally they're considered the average temperature. So there might be a little spot on a particular star that's hot enough to to ionize a little bit of helium, but not much. Okay. All right, so this is describing the lines, right? So for example, for the A stars, when you look at the neutral helium, the lines are very faint. You get some heavy elements. You get some very strong hydrogen lines. The heavy elements are singly ionized, and it just means there's one electron that's been stripped off. The next one is the F stars. Again, one electron has been stripped off of some of the heavier metals, and you get many neutral metals, and the hydrogen lines are relatively moderate. That is the intensity of it. And you can further. Here's some typical examples of some of these different types of stars. Like, for example, Rigel is a very well-known star. It's in the constellation Orion. Vega is a wonderful summer star. It's part of what's called the Summer Triangle. Anyhow, it's so Vega, of course, is a type star. Canopus is an F type star. Canopus is actually one of the besides the star Sirius, it's the second brightest star in the night sky. Notice the Sun and Alpha Centauri are both G-type stars. Arcturus and Aldebaran, which are very bright red stars in the night sky, are K stars. Betelgeuse and of course Barnard Star. Barnard Star, by the way, it just happens to be the second closest star system to us, but it's a very, very dim star. I mean, it's very. You have to have a pretty large telescope to be able to see Barnard Star. Betelgeuse, however you want to pronounce it, is a very bright red star. It's the one that's in the upper left-hand side of the Orion, the constellation Orion. There's actually been some interesting things that have been going on with Betelgeuse lately. It's dimmed significantly over the last decade or so, and so we're still trying to figure out exactly why it's dimmed. We'll talk more about that later. All right, so this is just converting from the magnitude to luminosity, and as it shows right here, if you go five steps in a change in magnitude, notice, like, for example, this, like, 1, of course, would be a 1 solar luminosity, and this is what we call the absolute magnitude scale. So again, I don't know if it's again, but the absolute magnitude scale is to what we've done is mathematically you put the stars 10 parsecs away, and you say, well, all right, if they're all 10 parsecs away, how bright would they truly be? And so that's called the absolute magnitude scale. So, for example, the sun would be about 5. So like in the night sky, without a telescope, you'd barely be able to see the sun if it was, or a star like the sun. Obviously, you don't want to put the sun 10 parsecs away. That would be devastating. But imagine a star as luminous as our sun, and it was 10 parsecs away. We would barely be able to see that in the night sky with the unaided eye. And so with that, in solar units, that its luminosity would be 1. So if you go to a brighter star, if you make a change in absolute magnitude of 5 steps to like a 0th magnitude star, that the luminosity would be 100 times that of the sun. All right? And the opposite is true, of course. If you go to an object that has an absolute magnitude of 10, from a star that would have an absolute magnitude of positive 5, it dims to an absolute magnitude of 10. Notice it would be 100th, 1 over 100 in luminosity compared to that of the sun. All right, and then if you go another 5 steps, it would, each 5 steps, it goes down by a factor of 100. All right. There's very few stars, by the way, where you can directly measure the size of the star. Betelgeuse is a large enough star, and with the Hubble Space Telescope, we can actually measure its radius, or we measure its diameter, and then of course calculate its radius. All right, but there's another method in which to find the size of stars. Right, it's important for us to know the size of stars, and so this is related to the following. Right, so like I said, you cannot This is an exception. There's very few stars that you can actually measure the size of them directly. And so what we generally do is we look at the fact that the luminosity is proportional to the radius squared times the temperature to the 4th. Remember, the temperature to the 4th is related, of course, to that's the Stefan Boltzmann equation. Where does this radius squared come from? Well, it turns out that if you increase, let me look at this. So just imagine. I mean, this is the star Betelgeuse, but think about these as spherical shells, and as the spherical shell, as the spherical shell gets further and further away from the star, basically the surface area of the shell increases as 4 pi times the square of the distance. So the square of the distance from the center of the shell, or of the star. So this is basically the inverse square law, right? It just tells you that the energy gets spread out as the square of the distance. All right, so luminosity is proportional to the square of the distance and the 4th power of the temperature. So there's actually a general division among stars. Notice our star, the sun, and most stars in the Milky Way galaxy and in other galaxies, as a matter of fact, are dwarf stars. It turns out. So if a star is the same size as our sun or smaller, it's considered a dwarf star.